Hello everyone, welcome back. So today we're learning about the areas under curves, kind of what they mean and also how to find them. For goals, is understand the relationship between the area under the curve of a graph or the graph of a function and the integral of a function. And also be able to use what's called a Riemann sum and then to estimate this area under a curve. So we're talking about the area under a curve, or more specifically, as it says, the area between the curve and the x-axis is a particular antiderivative of the or integral of the curve. Okay, so let's come over to the right for a moment. And basically what this says, if we have any kind of graph, let's say this is our, let's say we're going from the x-axis, or more specifically going like some point A to some point B, then what we see, if this is our curve, this is our f of x, okay, this area under the curve between A and B is the antiderivative. Okay, so the area is our f of x. And remember that it's an antiderivative f of x, capital F of x. Take the derivative of that, gives you small f of x. This is a particular antiderivative or integral. Okay. And we're going to see that. So basically, remember if you have some function, okay, think of this way. This is the small f is the derivative of the big F. So what the small f is doing is, remember, at any point on the small f, at any point value of x, it gives you the instantaneous rate of change of the function. So what happens if we add up all those changes from A to B, then that gives us an accumulation of all those changes. That gives us basically this antiderivative. Okay, that's what integral is, or an antiderivative essentially is kind of an accumulation. So a derivative gives you an instantaneous rate of change, and an integral is a way of adding up all those changes. Okay, so f of x gives the instantaneous rate of change at any x, and then the capital F of x, the antiderivative, basically essentially adds or adds up all those changes. Okay. And so a good example, as I mentioned here, my next point, the area under the curve of velocity or speed graph is actually the distance you've traveled. Let's look at that example. All right. So let's just do a basic one. Say you travel 50 miles per hour. I'm going to write like this, miles per hour, for 3 hours. Then if we graph that, in this case, the graph is simple because we're traveling at a constant speed. Okay. So here's our time in hours. And here's our velocity or speed in miles per hour. Oops, that should be actually HR like that. Okay. So if you're at 50 and base this is 1, 2, 3, okay. And base is just a straight line. This is our f of, we call it f of t, function of time, just a straight line. Okay. So if we add up, basically what we can think about is that if we add up that area under the curve, so f of t is equal to our velocity or speed. So the area under the curve is the distance traveled. Okay. And we can do this pretty simply. So if you notice, we just made 3 rectangles. Okay. Each rectangle has a width of 1. Okay. And a height of 50. So add the 3 rectangles to get the total area. Okay. Of course, we can also do this by 3. So basis is going to be, so 50, each one is 50 times 1. So 50, okay, times 1 plus 50. The height of each one is 50 times the width of each one is 1. Then plus 50 times 1. And of course, that's going to be 150. Of course, it'll also be the same if you just multiply 50 times 3. Okay. And of course, this case, this is 150 miles. Okay, so the area under a velocity curve gives you the distance you traveled. Okay, and that's true of any, essentially of any rate curve, any kind of rate, anything that's changing over time, that's what it does. Okay, now let's check this using distance equals rate times time. I hope you remember that formula, D equals RT, or distance equals rate times time. And you notice the rate then, of course, is 50 miles per hour times the time, which is 3 hours. And of course, our units here, the reason I wrote that way to cancel our units, we're in miles. So 50 times 3, of course, is 150 miles. Okay, so that's a good example, a basic example of how this works. Now, what if you have a more complicated speed curve? Okay. And you could. Actually, I need a little more space here. Let me go right here. Actually, go down here. There we go. Okay. Now, more general curve might look like this. So let's make a bigger curve. We'll explain it more. That will allow us then to explain how we're going to kind of find this area. So let's say you might have a different, this could still be time, okay, in hours, and this could still be velocity in miles per hour, but maybe it's not as simple, okay? Maybe we go faster and slower different places. It looks like this, okay? And here, once again, we're going to go between some point A and some point B, all right? What we can do is that area here is still the distance traveled. Under the curve, although it's a little harder to find, okay? This is our velocity. I probably should call it V of t in the other one. That's okay, velocity. All right, now how can we add that up? How can we find that area? Well, one thing we do, kind of a similar thing we did here. This is a lot easier since it was just a straight line, a constant function. We add up these 3 rectangles. We can do a similar thing and make rectangles here to estimate this, okay? So what we're going to do is let's make rectangles, all right? Let's divide this up, kind of up into parts. So here, we're going to call this x1, x2, okay? And then over here in the middle, we have like xk, and this is going to be at basically b. Here, a is going to be x0, and call this here xn. Okay, we're going to divide this up to n parts, and n can be whatever you want, how many you want. And what we're going to do then is we're going to make rectangles, and basically we're going to use the height where it meets the function as the height of the rectangle. Now, so let's say we do this, so we'll see it's called a left-ended. So I'm going to use the left end of our, where this meets our function, the left end, the height of a rectangle. So what I'm doing is just making these rectangles, as you see. Okay. And we have several through here. And they should all, in this case, all be the same width, but in general, don't really have to be. And if you notice also what's happening is that although we're making these rectangles, it's not working out perfectly, as you can see. Sometimes our rectangle goes above the function, sometimes it goes below, okay? And that's part of the issue. But what we can do then is we add up these rectangles, add up the area of these rectangles, and that will approximate or estimate the area under the curve, okay? As you see, not perfectly. There's some issues there. And we'll talk about how to improve that, but that's the idea, okay? So going to add up the area of the rectangles. Okay. Also, one more thing. We're going to call each one, we're saying that each one has a width we're going to call delta x. Now, in general, these widths will all be the same, but here, for simplicity, all these rectangles have the same width, just different heights. Okay. So if we add that up, what we do is we'd have basically right here. So the height of our first rectangle, the width is delta x, the height of the first rectangle. The way we've done it, once again, this is not the only way to do it, is we made it here at the left edge. So basically that is x0. So basically call this v, but f, v of, let's go back and call it f just to be consistent. Be consistent with also what I'm about to show you. So let's call it f, though it doesn't matter. Well, it's f of t for our speed. So f at x0, basically at a, okay, where that first one is. Once again, we could choose our height at anywhere in this rectangle, which shows at the left end, then times the width of that rectangle, okay? So this is the area of that first rectangle, the height, which is f of x0, okay? And this one, for example, is f of x1 and so forth, okay? Now the second one, of course, our height is going to be at x1, so f of x1 times the width, which is delta x. We call that the width, okay? Then plus, then somewhere, then we get all the way down to, of course, we also have our xk, where that is. And then go all the way down the end, and basically, we have right here, this is actually f of x to the n minus 1. Since xn is the very end at b, this is going to be x to the n minus 1. That makes sense. But the idea, you get the idea here. We're just the x to the n minus 1. We're just taking these values. So if we do like 10 intervals, this is like f of x of 9. This is x of 10 at the end. So x to the n minus 1 times delta x. And that is the area approximate. There's the, once again, the estimated area under the curve. The estimate, not the true area, but the estimated area. Okay, that's one way you can actually approximate this area. And this has a specific name. This is something called a Riemann sum. Okay, so this is what's called the Riemann sum of the area under the curve. Okay, named after a mathematician named Riemann, but it's sum. So let's look at this definition of the Riemann sum and see if this kind of makes sense what we just did. And also we'll show you a better picture here in a moment as well. So the Riemann sum is the sum of the areas of a set of rectangles used to estimate the area under a curve. That's what we just did. Okay. The width of each rectangle is called delta x. That's what we said. And basically you get delta x. We'll show you how to do that in a minute. Height of each rectangle is the value of the curve or the function value at where each rectangle intersects or crosses the function. Okay. So based in mathematical terms, if we say it that way, we say, suppose you have some function f. This is defined on a closed interval a to b. Okay. We divide it into n subintervals. It can be whatever you want. 10, it could be small, it could be 5, 10, 13, whatever. Okay. And the way we do that is we take the limits of our interval, b minus a, that's the width of our interval, the length of our interval, divided by n, that divides it to n equal parts. That gives us our delta x. That's the idea here. Okay. Then we take this x, k, and this little star right there as any point in this interval, x, k minus 1 to k. So that can be anywhere in between here. Okay. And basically just has to be somewhere. You just have to evaluate your function either at the end point, the end of your rectangle, or somewhere in between. Doesn't really matter. Okay, it has to be somewhere. Then what this shows you is just simply, as I just said, we're adding up. We're going to take the function value is the height of each rectangle, delta x is its width, and we add all those areas up and get the total. And hopefully you've seen this before. This is called the summation notation. What this says, I'm going from k. So if k is start with 1, when k is 1, you get this first term, x1 prime, delta x. Then the sum means plus, and we add the next term. So k then goes to 2. So here we have f of x2 star times delta x. Then all the way up to whatever k is. Okay, then finally we get to n. K goes through all the numbers up to n, and when k is n, we get the last one, f of x to the n delta x. That's what's called a Riemann sum. And that is a way to actually add up or estimate the area by adding up, creating these little rectangles, adding those areas up. And actually, we'll see in a future video, that's how we actually define what's called the definite integral later on, is using the Riemann sum. Now, let's look at a picture of that. This may be a little hard to see. You may have to enlarge this a bit, but basically it shows you exactly the same thing I did. So let me do something a bit. Let me actually, some of the rest of this, let me actually make this larger. And we'll go back to our regular view in a moment so we can see this good. Now, take this picture, took these pictures from a textbook. It shows basically what I was saying. So for some function, f of x, we want to estimate the area under the curve from A to B. So we call A our x0. And once again, we find our delta x from taking B minus A, that length from B to A, divided by n, where we want n to be, is our delta x. So each of our rectangles, we have the same width. And the height of the rectangle is where it crosses the function, where it intersects the function. And where in that between each x value is up to you. Okay, so from x0 to x1 is the width of our first rectangle, x1 to x2 is the width of our second rectangle, and somewhere where it crosses the function curve, it chooses our height. It can be anywhere in between the left end, the right end, or anywhere in between. The most common ones are the left end, the right end, or the middle one. Okay, and we do that, and once again, here's in general our k. So here's x of k and k minus 1, and our value, we choose x of k somewhere in between, and that gives the height of a rectangle. Then we add all these rectangles up, that approximates then our area. Okay. Now, a few more things to mention. This x of k star, that's where we actually get the height of a rectangle, where it crosses the function. And like I said, the most common ones are left, right, and midpoint. So if you use the left endpoint, like right here, see if there's one here that's like that. This one right here is approximately, looks like about the right endpoint. So, or that left endpoint, that'd be called a left Riemann sum. If you use the left endpoint. If you go from the right endpoint, so there's one, this is sort of close to being right endpoint. So that's the right endpoint of your rectangle. And if you use the midpoint of your rectangle, that's called a midpoint Riemann sum. And in general, it doesn't matter which one you do, because as we'll see in the future, we're going to talk about a limit of these things all go to the same value. That's the idea. Okay. Now, this graphic here just shows those as well. So left Riemann sum, we're taking the height of our rectangle to be the left side. Okay. And once again, you see there are gaps, see places where the rectangle goes above the function and below the function. So it's not a perfect estimate. Okay. No matter which way you use, you never get a perfect estimate. Okay. The right Riemann sum, we use the right side of the rectangle where it meets the function as our height. And the midpoint, where the midpoint of our rectangle meets the function as our height. But still, they all have gaps and all have places where it overshoots and undershoots. Now, a few more things or a few notes. As you can imagine, then, the smaller the width of each one of these rectangles, and the more, which means the more rectangles we're going to use, the better estimation of the area of the curve becomes. Okay, so if I make these rectangles smaller widths, then actually I reduce these errors, these places where it overshoots and undershoots, the more rectangles I use. Okay, and that's what you can see right here. So this is also taken from a textbook. So if we try to find the area under the curve of basically t squared or x squared, okay, and this also means velocity and time. All right, if I use two intervals, are called subintervals, you can see, not very good, but that's how it would work. If I use 4, that's better, okay? I've reduced the error, the undershoots and overshoots, but still not great. Now, if I do 8, you can see it's improving. And this last table here, once again taken from the same textbook, shows what happens to the area as I increase my number of, basically reduce the width of my rectangles, increase my number of these subintervals, increase the number of rectangles, okay? So at 2, the one I just showed here at 2, the value is approximately 160. If I go to 4, 168, and 8, 170. Notice here if I go to 64, so we're doubling each time. And you notice it's kind of settling down as basically a limit, and as we'll see in the future, this is related to a limit. And basically, it's limiting to this value about 170.656. And if we use more rectangles, do it correctly, we'll basically kind of have the same one prove the value, but not by much. Okay, we're still going to be based at the same name. We're just going to prove our decimal places out here. All right, so that's the idea of how a Riemann sum works. And basically you do that. And once again, the more of these you use, the more of these rectangles you use, the better. And one more thing, we'll shoot an example like this in a moment. If your curve is above the x-axis, the area is positive. And if the curve is below the x-axis, the area is actually negative. We'll see how that impacts things here in a moment. So let's put this back where it was. What else do we do? Oops. Hang on a minute. I'm trying to. There we go. Okay. So after saying all that, let's look at some examples. Practice with a few. Let's put the definition back up here. Okay. Yeah, let's take a look at a few examples. All right. The first one, I was going to talk about velocities. That's a good place to start. That's something we're all familiar with, how this works. So velocity of an object moving along a line is given by v equals f of t on this interval from 0 from t to 8. Okay, you have the figure below. This one's going to take it from a textbook, where t is measured in seconds. Of course, t can be in any units of time. And also your velocity can be, in this case, feet per second. There could also be any other units of length divided by time. So it's dividing the interval into two subintervals, 1, 0, 4, then 4 to 8. That's what we see right here. So the first interval goes from 0 to 4, second one from 4 to 8. And then assume the object moves at a constant velocity equal to the value evaluated at the midpoint. So here we're doing a midpoint sum. And basically we want to approximate this, and then we're going to do the same thing for 4 intervals. Okay, so basically use the picture as our guide. So the first one, we're dividing this up into two, using 2 rectangles. And then the second one, we're going to divide it up into 4 rectangles and see how our actual value improves. Okay, now let's take a look at that. So part A, all right, so we're just going to, let's take a look at so our delta x is going to be, well, first off, and back up our n, our number of subintervals for the first one is equal to 2. And so that means our delta x is going to be, if we follow our formula, so b to a, we're going from 0, 8 to 0, 8 minus 0 over 2, and delta x is 4, as we can see. Okay, now if we do that then, so let's add, so the area under our curve, the estimated area, in fact, let me call it the estimated area, because it's not going to be exact, as you can see. The estimated area, okay, and once again here, we're also using a midpoint. Riemann sum, just abbreviate the midpoint, evaluating at the midpoint. Okay, so the height of our first rectangle is 40. And I put the units here as well in the first one anyway. 40 feet per second times the length, which is 4 seconds. Of course, the seconds will cancel out. And then our second rectangle, the height of the midpoint we're using is, looks like 70. So that's 70 feet per second times also 4 seconds, the same width. Seconds cancel out. And what we have then is going to be 40 times 4, it's 160. And once again, that's going to be in feet. If the seconds canceled out, plus 70 times 4, which is 280 feet. And if we add that together, it'd be 440 feet. Okay. And so that's also the estimated area, and that's also the estimated distance that was traveled, 440 feet. Okay. Now, as we can see, it's obviously not very good because we have some, missing some cases. We're overestimating it right here on top of the curve, below the curve, we're missing that, below the curve and above the curve. So that's not going to be perfect, but let's see what happens if we do go to 4 subintervals or 4 rectangles. Okay, so part B, it's going to work exactly the same way, except we're just doing more. So this time we're doubling the number of our rectangles or subintervals. N equals 4. That means our delta x, the width, is going to be same numerator because we have the same curve, and then divided by 4, and that's going to be 2. Okay, so I have to, so once again, the area, I'm just call it the area, this time's an estimated area, or the same as the distance traveled. Okay, so it's going to be the first one, looks like it's going to be evaluated, and as you can see, these are both, of course, the same curves, just done differently. Looks like about 30. And I'm not going to put the units this time because we just saw that. So 30 times 2 plus the second rectangle. Looks like 50 times 2. So the height is 50, width is 2. Plus 80 times 2. 80 is the height of the third rectangle. Plus, and this one is 40. So height of the fourth rectangle is 40 times 2. Okay, and if we combine all that, and actually we could just factor the 2 out. And so we have 30 plus 50 is 80, plus another 80 is 160, plus 40 is 200, times 2 is going to be 400 feet. Okay, so now this is more accurate, as we can see. Now we don't know exactly what our true answer is. Of course, we know as we see that the way we can do that, though, is actually use more and more rectangles. But this one is, the second one is going to be more accurate because the amount of overshoot and undershoot, part that's above the graph and below the graph of rectangles, is less. Okay. All right, now this one, what we want to do is we actually want to do kind of a similar thing. What we want to do, though, is actually going to compare using a left and right Riemann sum. Okay, so remember what that says. So the left Riemann sum is where we take our values from the left endpoint of our subinterval or rectangle, left side of a rectangle, and then versus the right side of a rectangle. So we're going to compare these, see what we get. Okay. So let's kind of divide this, call it A and B again. Okay. So for part A, if you notice, also our interval is going from left to, so we're going from 1 to 5. The interval. Okay. And this one, in both cases, that's true in both cases, our n is equal to 4. Okay. So actually, our delta x and everything is going to be the same. So I'm going to just get rid of the a. This is going to be true for both. Okay. So then our delta x is going to be 5 minus 1 over 4. That's going to be 4 over 4. That's going to be 1. That makes everything simple. Okay. We have a width of 1. All right. So for part A, let's label these as A and B. So A, the left Riemann sum, I'll also abbreviate that. Okay. So we need to evaluate that each one at the left endpoint. Okay. Now, and so that area, once again, this is the estimated area, is going to be f of, let's write kind of more formally, f of 1, right? Starting at 1, that's where we evaluate at 1, times delta x, plus f of 2 at 2 for the second rectangle, times delta x, plus f of 3, right, at 3, that's the height of our third rectangle, times delta x, plus at 4, so our fourth rectangle, we're going to the left side, which is at 4. So f of 4 times delta x. Okay, now we do that. Of course, we know our values. So at 1, remember our function is 1 over x, and that's going to be 1 over 1 times 1. That's easy. That's just going to be 1. Then 1 over 2 times 1 plus 1 over 3 times 1 plus 1 over 4 times 1. Okay. And so that's going to be 1 plus 1/2 plus 1/3 plus 1/4. And basically, if we do the math here, it's a little bit of a pain. In fact, let's just use Desmos for that. We'll just approximate it. You can do this by hand, but there's no need to do that here. So let's just go to Desmos. Use Desmos anyway. Remember, you can also use Desmos as a calculator. So I'm just going to do that. So type 1 plus 1/2 plus 1/3 plus 1/4. And of course, you can get an exact answer. This is approximate, about 2.08. Okay. This is approximately 2.08. Okay. Now, so that's the left Riemann sum. Now, the right Riemann sum actually just 1m for sum, doing exactly the same thing. So this time we're just taking our functional inputs from the left side. Okay. So the area, you write it that way. Okay. Let's see. So first, remember, everything is going to be times delta x, our width of a rectangle. Our first rectangle, instead of going from the left endpoint of our interval, remember 1, we're going to go from 2. That's where it meets the curve at 2. Okay. F of 2 plus f of something times delta x. Let's see what that is. Okay. So this time, the second rectangle, it intersects it at 3, and the fourth one at 4, the third one at 4, the fourth one at 5. Okay, so you get the idea. 2, 3 plus f of 4 delta x plus f of 5 delta x. Okay, and of course, that's just going to be f of 2. Remember, a function is 1 over x, so 1/2 times 1 plus 1/3 times 1 plus 1/4 times 1 plus 1/5 times 1. Okay, and of course, that's just going to be 1/2 plus 1/3 plus 1/4 plus 1/5. Okay, now once again, we can do that exactly, work the fractions, but just use Desmos to add it up. Be easier that way. Besides, we're just merely for comparison's sake anyway. So 1/2 plus 1/3 plus 1/4 plus 1/5. And yeah, that's actually quite a bit different. 1.28. Okay, so 1.28, so quite a bit different. Okay, so as you can see, there's quite a bit of difference there between those two. All right, which one's more accurate? It's hard to tell right now. In fact, we'll learn in the future, in future videos, actually how to actually do this, find the exact value, not having to use Riemann sums. But once again, if you use more rectangles, you get a better estimate of that. Okay. Now let's take a look at another example. In just a moment, let me decide what I want to do. Double check that's what I want to do. Okay. Now let's do one where I don't actually have a pre-made picture. Let's call this guess number 3. Let's say we want to do this. Let's say our f of x is x minus 1, and our interval is going to be 0 to 2. And let's say we want to have n equals 4. Okay. And let's say this time, let's use, well, let's say use midpoint. Let's graph it first and decide that. Okay. So x minus 1, so it's a linear function. from 0 to 2. Let's go to Desmos and see what that looks like. That's going to help us. So y equals x minus 1. Let's zoom in some. Okay. So we want to use 4 intervals. So intersect right here at 0, 1 and 1, 0. That point there is going to be 2, 1. So let me actually highlight those points. So 0, -1. Have to label these just so we can see them. So, and then 1, 0, where our intercept is. And the other point here at the top, right here, is going to be 2, 1. Okay, that'll help us get an idea what this looks like. Okay, so we can see what it looks like. So let's go back and graph it on our own. Let's make up our system and everything. Okay, so once again, this point is 0, -1. This point is 1, 0. And this point right up here is going to be 2, 1. Okay, now we want to do 4 subintervals or 4 rectangles. Okay, so n is equal to 4. Then our delta x, once again, is using our formula, is going to be b minus a, so 2 minus 0 over 4. And that's just going to be 1/2 or 0.5. Okay, so 1/2. So we're going to have rectangle here, 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 and here. So 4 rectangles. So first off, let's draw this function. And once again, it should be a straight line. Okay, now, this, of course, is at 1. This is 2. This is 0.5, and this is 1.5. Okay, now let's also decide. Yeah, I think I'll just do a right. Let's just use a right Riemann sum. Okay, use a right Riemann sum in this case. That's just a choice. All right, so our first rectangle is going to look like this. Okay, now oddly, our second one, if we just use a right, in fact, well, use a right Riemann sum, that's going to be confusing, I'm afraid. Let's actually change that. Change my mind. I just realized that actually, if we did a right round sum, which is perfectly okay, we'd actually have no rectangle at all right here or here. Okay, so that may look a little strange, but that can happen occasionally. Let's use a midpoint Riemann sum. A little more work, but that's okay. So midpoint Riemann sum. Okay, so rectangle. So our midpoint right here, it's going to come right there. That's our first rectangle. Okay, here's our midpoint right here. So our second rectangle. Okay, midpoint in between. There's our third. And our fourth. Okay, so we're using the midpoint. Of course, it's still okay to use the other ones, but we'd have no rectangles here at all, which can happen, but it may look strange. Okay, so now if you notice, in that case then, this, we have to evaluate this is at 0.25. This is at 0.75. This is 1.25, and this is 1.75. That's where we evaluate. Okay. All right, so we know the width of each one is 1/2, which is 0.5. And we know the height. So basically, our area, once again, this is our estimated area under the curve, the Riemann sum, is going to be f of 0.25 times 0.5 plus f for the second rectangle, f of 0.75, and that's the midpoint, times 0.5 plus f of 1.25 times 0.5, and then we'll finish it here, plus f of 1.75, the midpoint of the fourth rectangle, times 0.5. Okay, now what's each one of those going to be? So we can actually do that. So there's x minus 1. So 0.25 minus 1 is going to be negative 0.75 times 0.5. okay, plus 0.75 minus 1 is going to be negative 0.25 times 0.5. All right, the third one is going to be 1.25 minus 1, which is going to be 0.25 times 0.5. And then finally, the last one, 1.75 minus 1, and that's going to be 0.75 times 0.5. Okay, now we don't really even have to add this up because hopefully you can see what's about to happen. Is it basically, in fact, we can do this by hand. We can factor out the 1.5, 0.5 from everything. What we have left is negative 0.75 plus or minus negative 0.25 plus 0.25 plus 0.75. 0.75. If you notice, these cancel each other out. These cancel each other out. We're left with just 0. Okay. And y is what I mentioned before. So if you notice, this one is kind of symmetric. Our areas, these areas here are negative if they're below the x-axis. These areas here are positive, they're above the x-axis, and they came out in the function values. Okay. So added it up, and actually, that is actually 0. Okay. And if we think about this as you could possibly think about this in terms of velocity. If you remember, velocity is both direction and speed. So think of this as going in a negative direction for a while, then going in a positive direction for a while, and in the same way, kind of come back to your starting point. You can think of it that way. But yeah, so in this case, it just happened that worked out that way where it was 0. Now, if we'd gone instead of from 0 to 2, if we'd gone from, say, 1 to 2 or even 0.5 to 2, it wouldn't have been 0. Okay, it just happened to work out. But when everyone to see that is that can happen sometimes. Also, the fact that if your curve is below the x-axis, that means essentially that's a negative area, and that will be reflected when if you do it correctly in your function values, your heights will be negative, and then that part will actually take away from the overall sum. So it is also possible to have a negative integral if everything is below the x-axis, or if the kind of the bulk of it is below the x-axis. Okay, let's kind of review what we've learned so far today. So if you have like a curve that represents a rate, like a velocity curve, the area under that curve is based on the accumulation of that velocity. In this case, if velocity is distance, any kind of accumulation. That's what an area under curve does, is kind of adding up all the small changes. And we did that by a Riemann sum, where we created a series of rectangles and basically add up all those rectangles. That gave us an approximation of the area under the curve. We show there you can essentially take your height for each rectangle anywhere in your subinterval, anywhere in that width of your rectangle. Most common ones, though, are once again the left, right, and midpoint Riemann sums. Then also we talked about if the curve is below the x-axis, that's a negative area, and also the more rectangles you use, the more accurate your estimate is. Thank you. Have a good day.